All right, here's the third and final video, and I'm not sure what I did to my screen, but now it's black background, which might be interesting. Anyway, just to recap what we have been discussing so far, let's look down at the bottom here at these sets of equations. Again, these are all equations on your equation sheet. So again, first off, we defined how to calculate work. Work is the average parallel force exerted over some distance. So the F and the cosine theta together make the parallel force, and D represents that distance. We talked about positive and negative work. So if the force and the displacement are in the same direction, it's positive work. If it's in the opposite direction, it's negative work. If it's perpendicular, it's zero work. Then we started to define the different types of gravitational potential energy, basically using the idea that area under a force versus position graph is equal to the work done, which is equal to the change in energy. So we kind of derived an expression for the gravitational potential energy, which is equal to the mass times the gravitational field strength, which together is equal to the weight of the object. And then we had any kind of change in height. Typically, we tend to make our initial height equal to 0. So the gravitational potential is just at that location at height. The spring energy equation, or the work done by an external force, is going to change the energy of the spring. And we get 1/2 k delta x squared to calculate the spring potential energy. Work done by a net force will equal the change in kinetic energy, and kinetic energy is equal to this translational kinetic energy that we started out with, which is 1/2 mv squared. And then we talk about dissipated forces. That would be thermal energy, or dissipated energy, or internal energy would just be the force of friction times that distance. Again, this is the work equation right here, force times distance. This equation is not on your equation sheet. It's really just a variation of the work equation there. And again, thermal energy is always going to be negative work being done because you're always going to remove energy out of the system. And then just to review, the force of the spring is equal to the negative displacement of stretch or compression times the spring constant. Notice that spring energy and force of the spring are two different equations. They look very similar, but energy is not the same thing as a force. They are separate. Remember, work, which depends on energy, force times a distance, that's equal to a change in energy. So that was kind of our other big idea. So what we're going to do is talk some pro tips, talk a little bit about mechanical energy, some tips about gravitational potential energy, and then I'm going to ask you to do these example problems on your own. All right, so picking up where we left off, we finished our review there. Mechanical energy. So mechanical energy is typically abbreviated ME for mechanical energy, and mechanical energy is the total amount of potential and kinetic energy. So mechanical energy would be equal to spring potential energy, if there's any spring involved there, plus any gravitational potential energy, plus our translational kinetic energy. So this is what we kind of call mechanical energy. It's just specifically, basically, it just doesn't include dissipated energy. It kind of includes almost everything else. And any kind of work done, if we have any work done by an external force, it will change the mechanical energy of a system. So that's important to remind us, like work being done is going to change that mechanical energy. All right, so let's just give a couple of tips about gravitational potential energy. One of the things we want to make sure that we do, because again, we're really only going to be interested in the change. So we want to choose the lowest vertical position to be gravitational potential energy equal to 0. And then we will measure our gravitational potential energy relative to that point. Again, this is going to be just convenient for problem solving. All right, our second pro tip about gravitational potential energy is that gravitational potential energy is what we call path independent. So it's only the change in vertical height that matters. And I'll give an example of what I mean by that in a minute. All right, so let's just do a quick example. So this is, let's call this our ground level, and this is our gravitational potential energy equal to 0. I could take a ball here and just drop it from some height here. I'll say this is my initial height y, and have it go straight down. And then its change in gravitational potential energy is still going to be m times g times any change in height. And if that's 0, then basically I'm just looking at where it started. I could take the same block here and let it slide down a ramp. As long as this ramp is still the same y height, it will have the same change in gravitational potential energy as it goes from the top of the ramp down to the bottom of the ramps, right? So again, this is what we mean by the path independent. If it goes down the ramp, it is the same gravitational potential energy as if I dropped it. So taking that like one step further, I could keep that block and put it on some kind of really weird loop-de-loop slide and have it do all kinds of crazy things and end up here. As long as this change in vertical position is the same as all the others, this block still has the same change in gravitational potential energy. So this is what we mean by path independent. It doesn't matter how it goes from its initial vertical position to its final vertical position. We're just looking at the change. All right, the rest of this is going to be up to you. I want you to try doing examples 5, 6, and 7, using some of the information we've used, also connecting it to your notes. Don't just go at it alone. And again, show full solutions, so show all steps. And we will whiteboard these when we get back together on Wednesday.